I mean, it is said by the YouTube, but okay, now it is recording. So sometimes there is a gap while I'm talking with the YouTube streaming. So next time maybe I should not forget. So it is both streaming and recording. Okay. So let's see in a few. I'll see in a few minutes. Some universities cancel their whole term for teaching. Really? They can't do that because they need a permission from Higher Education Council. Those universities are American universities as far as I know. Gökçe, what university did this? Anyway. Okay, this coffee is too cold. I need to get some coffee.
Baksana yine beyaz beyaz duruyor.
Aa, burayı yıkamışlar ya. Bu ne ya? Evet. Hani Gökçe göremiyorum öyle bir şey burada ben ya. What? Okay, let's start. Is everybody ready? Type yes. My health is poor. What's going on? YouTube is not receiving enough data. Okay, we will read it later. Okay, yes, good. So, stream settings, analytics, chat rate. What is the viewers? Okay, good. Okay, so TSL is a special instruction supported by the CPU, and it does this. It reads the contents of the memory word into a register and then stores a non-zero value to it. So this is what you do. Instead of calling this enter region with the process number, okay, you only just call this simple function enter region. Remember, note that you don't send your process ID. You just say that I like to enter the region. It says that, okay, load, copy the contents of lock to this register and put a non-zero to lock, and compare the value of lock against 0. Okay, if not equal, go to enter region. So busy wait happens here. Okay, if not equal, that means that if the loaded value from the lock is not 0, then that means that somebody has the lock. It should be 0. I like it to be 0. Okay, if it is not 0, then I will wait. I will do this again and do this again and do this again until I get the lock value of 0. Okay, since if the lock is not 0, if it is 1, my register value will be 1, right? And I will compare 1 with 0, so it is not there. And again, when I go back to top of the loop, I will do the same thing. And since lock is not 0 at the beginning, doesn't matter if I store a lock value of non-zero value to there. And at the end of the critical region, I just move 0 to lock. Okay, so if you have the TSL instruction, you don't need the Peterson's algorithm. You don't need a double lock mechanism. It all works. Good. So again, that's a many times we will say this. If we cannot solve a problem efficiently with our operating system, we will ask help from the CPU, from the hardware. Okay, so we will ask the hardware to do something for us. If it is possible, the new CPUs will support it. If it is not, then I have to do it the tough way. Okay, so at the beginning, the CPUs didn't have this TSL. Now they have it. At the beginning, the CPUs didn't have the virtualization support. Now they have it. At the beginning, the CPUs didn't have support for the hyper threading, more than one thread happening at the same time. Now they have it. Okay, so most of the time, the changes for the hardware comes from the operating system designers. Okay, another instruction alternative to TSL. I think the TSL is patented. Not everybody can use it. Intel uses exchange instruction. Exchange is supported by Intel CPUs. Exchange supported by the Intel CPUs. Exchange does this. When you say exchange register with a lock, it does exactly this. It copies the contents of the lock to R0, R0 to lock. Okay, and it is done at the same time, indivisibly. Okay, it cannot be divided into two. And if I like to implement the same thing with exchange, this is what I do. I move 1 to register, then I exchange the register value with the lock, and I compare the register value with 0. If I get a 0 from the lock, that means that I can go to my region, critical region. Otherwise, I need to go to the top of the loop, jump not equal. Okay, so very similar. Idea-wise, it's very similar. Okay, good. Any questions so far? So the spin locks, like this one, or this one, or this one. The spin lock is here, right? Here's our spin lock. Are the techniques that we have used so far to handle the develop solutions for this critical region idea. Okay, that was a spin locks. Okay, test and set lock, Peterson's algorithm, or any other type of solution. Spin lock. Okay, spin locks are good, but I mean, for really very long periods of time, it's not a good idea because you are wasting your CPU time. You test it, you go to the beginning, you test it, you go to the beginning. I mean, if I do this only a few times, that's okay. Only a few times, that's okay. But if you are doing this millions of times, that's waste of CPU time. That means that the other processes are spending so much time in their critical regions, depending on your application. It is okay. I mean, you may have to wait, but while you are waiting, you are wasting your CPU time. That's not a good thing. Because if you didn't waste your CPU time, maybe the other process will quit from the critical region in a short amount of time. So let's look at this problem. Acceptable for short waits, especially on multiprocessors, but for longer ones, we need a solution that says, I'm going to sleep. If this happens, you'll tell the operating system that I'm going to sleep until this lock is ready. Okay? let's try to design something for our operating system to eliminate the spin locks, or at least to reduce the effects of the inefficiencies of the spin locks. Okay, that's one thing. Okay, we need to be careful about actually spin locks a lot. One for efficiency, the other one is there is a very serious problem for this one. It's called priority inversion. Okay, priority inversion. Let's say I have two processes, process L and process H. Okay, why I have chosen these two letters for them will be clearer. Let's say process L has a critical region. Let's say this is start critical and end critical, and process H again start critical and end critical. They have both critical processes, and the reason why I am calling this L and H is this: H has a higher priority, L has a lower priority. That means the operating system will let H run, if it is runnable. Okay, L will never get a chance to run if H is runnable. Okay, L runs only if H is blocked. Let's look at this one. Okay, this is what I said. L never runs if H is runnable. Let's say while S is sleeping, okay, H is sleeping, let's say, the low priority process L grabs the spin lock. Okay, it says that, L says that I like to get the lock, and it gets the lock. Okay, and it is inside this critical region somewhere there. Okay, it's running the critical region. And then H wakes up while this one is in the critical region. H wakes up, it tries to get the lock using this one or this one. It will say that I like to get the lock, and I am in a spin lock, in an infinite loop. H will run. If there is an interrupt happens, the operating system will check if anybody else is ready to run. L is ready to run, but I cannot let L run while H is runnable, and it will let H run again. H will run in an infinite loop, and L will never find a chance to run so that it can release the lock. Okay, H wakes up and tries to get the lock. It spins, waiting for L to free it, but L can't get the CPU, so it doesn't progress. So L will be interrupted in this critical region. L cannot, although it is ready to run, operating system will never let it run. Okay, because H is runnable, but H is running something stupid. It is running this infinite loop. Okay, so this is called priority inversion. Why they call it priority inversion? It says that in this case the priority of L is higher, because without L running, finishing its job, H cannot run, but the operating system thinks that H has a higher priority. Okay, this is just one example of a deadlock. And if we have time at this end of the semester, we will look at this. Deadlocks. Okay, priority inversion is an interesting problem, and it can happen with the spin locks. Okay, because H never sleeps. It says that I will run. Eventually I will get the lock, but there is no way it is going to get the lock because lock is held by the L. Okay, so what I said was spin locks are bad for efficiency. Also, they are bad for these kind of problems. Okay, so let's try to find a way to eliminate the spin locks. Okay, simplest way is sleep and wake up. We need system calls. Okay, instead of going to the top of the loop, you tell the operating system that I will go to sleep until this lock is ready, until I can get the lock. Okay, so in an example, I am going to introduce this problem, producer and consumer problem. It's a very classical operating system inter-process communication problem, producer-consumer problem. A very typical example is the Prince spooler. Remember the Prince spooler that we looked at? Let's go to there. Yeah, this one. Spooler is a consumer. This is a consumer. This one is a consumer. And these two are producers. Okay, so these are consumer and these are producers. What we mean by producer and consumer, process A says that I like to print something, process B says that I like to print something, and this one serves them, it consumes them. So this is a typical producer-consumer example, and let's make this more general. We say that producer wants to add elements to bounded size buffer, and buffer is, if the buffer is pulled, the producer must sleep. Consumer wants to remove items from the buffer, and the buffer is empty, consumer must sleep. Okay, of course there is a buffer problem here, and also there is a race condition if you are not that careful. Okay, any questions? Is this priority handling yeah, operating system has to support the priorities, yes. Okay. Cosmos, I don't know what you mean Türkçe'ye geçecek miyiz? No, of course not. Let's look at this problem more carefully. We will produce something and we will put in a buffer, and if the buffer is full, I have to sleep. For the producer side, for the consumer side, if the buffer is empty, then I need to sleep. I don't go into an infinite loop. Emre, according to what operating system decide to process? Well, remember what we did last time. Okay, of course, this is my stupid Linux emulation. When I say AX, where is my AXP? I forgot how to get the priorities when I said the AF. Do you remember the option to get the priorities? Okay, low priority, kernel switching priority, I think minus Y. What was the option? Minus Y? Y? No. AXY? P? I forgot. Remember when I say there is an option that tells you the priority of the process. The priorities are set by the operating system, or sometimes it is set by the user. Remember this nice? When I say nice ls, I am running this ls program at a lower priority. So the operating system has to support it. PS minus AL. No, PS minus AL doesn't tell you, does it? PS minus AL. Yeah. This is a priority. See, this is a priority. If I run another bash with a nice, and when I say PSAL, yeah, this my bash, the second bash has a priority of 80. The first one, the second bash has a priority of 70. Since I am launching my PS with the second bash, is priority 72. So Windows is supporting these priorities. operating system has to support it. Can we say that my program lower priority? Nice is a way of, yes, of course. Nice is a way of changing your priority. But nice is a one-way priority change. It only lowers your priority. Usually, operating systems doesn't let you make your priority higher. It's an administrative privilege. Okay, good. So let's look at this example. And let's say we have n number of elements in our buffer. Count is 0. This is my producer. That is the program trying to print something. This is the consumer. This is the spooler. While true in an infinite loop. Okay. I produce an item. Whatever it is, just a regular thing. It produces an item. If count is n, that means that my buffer is full. I need to go to sleep. I need to wait. If count is not n, that means I have slots available. I insert my item. And then at the end, if the count is 0, that means that the buffer was all empty, okay, before I insert anything. I wake up my consumer. But what do I mean by that? If the buffer was empty before I inserted anything, that means that no consumers are active, right? They are all sleeping. So I am waking the consumer. The consumer just does the opposite. If the count is 0, there is nothing to do. I need to sleep. Okay? If the count is not 0, then I remove the item. Okay? If the count is n, that means that the count was n. Since the count was n, then that means that the producer was asleep. Then I need to wake the producer. Then after that, I consume the item. So in fact, what's happening here, that one of them is in an infinite loop. It is producing something. One of them is just producing something. The other one is just consuming it. But it is not as simple as running two infinite loops. You need to put them in a special buffer, and you need to take care of how the buffer is full or not full. Okay. Oh, I have a question. Yasir. Are spin locks common practice in any modern systems, or they are obsolete? No, they are definitely used a lot. Why? Because you don't want to make what is the alternative for the spin lock? You need to tell the operating system that you need to sleep, right? That's a system call. System calls are expensive. But if you know that if I take a few loops in a spin lock, let's say 5, 10, 100, that would be much faster than making a system call. Okay? That would be much faster than a system call. So if I do maybe 100 times a spin lock, after 100 times I would say that that's enough, I am sleeping. That would be a much better solution. So the pure spin locks are not that used much. Okay? But a hybrid solution that uses spin locks plus the sleep, wake up system calls are used a lot. Mustafa, it is ring buffer. It could be, yeah, but it doesn't matter if it's a ring buffer or a open-ended buffer. Doesn't matter. All you have is just n number of slots available. The number of available slots are not infinite. Okay, so I need to be careful. So this is a typical producer-consumer code, but as the title says, there is a race condition. Okay, there is a race condition. What is the race condition? Race condition is this. Let's say I am checking this one. I am running this one. If count is 0, I saw that the count is 0. Then I am going to sleep. Okay? Then I am going to sleep. If count to 0, then I am going to sleep. That's what I am going to do. I get an interrupt here, just at this position. Before I go to sleep, I get an interrupt. Okay? And my producer started running. It produced an item. Count is not n, count is 0. It inserted the item. Okay, it inserted the item, and it said that the count is 0. I will increment the count, and I will wake the consumer. Okay, it said that I am incrementing the count, and I am waking the consumer. It sent a wake up call to the operating system, and operating system took this call and said that nobody is sleeping, so I will ignore this one. When the context switch happened again, when I come to this one says that I'm going to sleep, and operating system says that, okay, you go to sleep. So this one starts sleeping, and this one thinks that it sent a wake up signal to the other process. So at the end, this one started sleeping, and this one is never going to wake it up. Okay, so there is a race condition. So if the interrupt happens here, there is a problem. The same problem here too. If interrupt happens right at this position, okay, two problems. Right this position, interrupt. If the count is n, I'm going to sleep, but before it goes to sleep, let's say context switch happened, and it says that, okay, count is n, I will decrement it and I will wake the producer, but operating system says that nobody's sleeping, so it is ignored, but this one goes to sleep after the context switch. So we need to do something about this. Of course, what we can do is, before checking the count and going to sleep, maybe I can say use a TSL instruction. Maybe use just something like this. Okay, enter region, leave region. We could do that critical region thing, right? We say that, okay, let's put this. Let's say that, okay, this is my beginning of the critical region and end of the critical region, beginning of the critical region and end of the critical region. If I do that, then I can prevent that kind of no. Beginning of the critical region is here because I'm checking it there, right? Okay, so maybe I can prevent it, but there are better ways of achieving this, standard ways of achieving this, and we are going to see this. Okay, and we need to handle the buffer size, also the mutual exclusion, etc. with this solution. Okay, good. Let's move on then. The solution. Okay, as I said before, I can solve this problem using the. Using this solution, TSL solution, or the exchange solution, no problem. But I like to use standard ways of solutions for this. That's one thing. The second thing is that, remember, our TSL and exchange solutions, they are spin locks. I am trying to prevent spin locks in this solution, right? I don't want to use those kind of spin locks. Okay, so let's see what people have found. Okay, we are going to use semaphores. The name semaphore looks like it is something sophisticated, but semaphore is a simple integer, right? When I say I have a semaphore, let's say S1 is just an integer. Okay, and since they are integers, there are operations that you can do on them. There are only two things that you can do with the integers, okay? In this case, either up or down. Let's say at the beginning it is 0. When you say up, it just increments the value by 1. When you say down, it just decrements it by 1. But I don't increment or decrement these using the regular operators. I ask the operating system to decrement and increment it. Okay, so you need to make a system call, or you need to ask your threads library to make this incrementation and decrement. What does down do? Down does this. Decrements the semaphore variable if it is greater than 0. If it is 0, it is doing something else. But if it is greater than 0, let's say its value is 5, it just decrements it. That's it. If the value is 0, it just goes to sleep before doing the decrement. Okay, since it is 0, it's not going to decrement it. It says that, okay, since it says 0, I will go to sleep before I decrement it. That means that somebody is going to wake me up. When I am waken up, I will decrement it later, and in that case, my semaphore will be greater than 1. Okay, so all this check, decrement, and sleep are atomic. It is done supported by the operating system. So down is regular down, regular decrement. If it is not 0, it is regular, no problem. If it is 0, it says that I am going to sleep before the decrement. When I wake up, I will do the decrement later. Okay, but this decrement will never make this S1 a negative number. Okay, up is something similar. Increment the semaphore. Okay, it just increments the semaphore. If a process was sleeping on it, wake it and let it do its decrement. It says that I am incrementing this one. Let's say S1. I am incrementing it. If anybody is waiting on it, if anybody is sleeping on it, I will wake them up. Okay, so this idea of semaphores are very nice. They generalize well to multiple users. Okay, multiple processors, etc. And 1965, it is used a lot by the operating systems, thread libraries, process libraries, etc. Okay, and we are gonna implement this producer-consumer problem using this semaphores. Since I have the semaphores, I will use down and up to count the number of slots available in my buffer. Okay, that's what I'm gonna do. Also, I need to use a binary semaphore, that is a semaphore that can become only 0 or 1 to achieve my critical region. Okay, any questions about the semaphores? They are not complicated. They are simple integers, you can think, and they are managed by the operating system or your threads library. Okay, they are used for incrementing and decrementing some values. The thing is that for the decrementation, if the value is 0, it doesn't decrement it. It goes to sleep before the decrement. It's going to decrement it anyway, but when it decrements it, it's going to be greater than 0. Okay, to make it greater than 0, it goes to sleep before that. Okay, and wake up up is something similar. It says that I'm going to increment it. Okay, after I increment it, if somebody is waiting on it, then I will call that one. I will wake up that one. Okay, so we could use the semaphore as a tool to implement the critical regions. Let's say my semaphore is it's an integer. Let's say this is an integer. Just decrement this integer. Since it's a 1, it just decrements it. I entered my critical region, and after I am done with the critical region, I just increment it. If it is 0, let's say if it is 0, when I say decrement this value, I cannot decrement it. I need to go to sleep. Why? Because it is 0. And I will not wake up until that mutually exclusive semaphore becomes greater than 0. When it is greater than 0, I will wake up. Operating system will wake me up, and I will decrement it. I will enter my critical region. So as long as I have my mutually exclusive variable as 1, I can enter this critical region. But once I am in the critical region, nobody can enter it because I decremented it. Yasir says that our up and down are system calls. Depending on your implementation, I mean, pthreads library, if your threads are implemented in the kernel space, then you can say that these are system calls. But most of the time, they are implemented by the libraries, and you handle these kind of things without going to the operating system. But it's an operating system thing, and it's a library dependent thing. Okay, good. So this is just one way of achieving critical region. What is the advantage of this over the TSL exchange instructions? implementation of the spin locks. Of course, these are much more efficient. Why? Because when I enter the critical region, if it is available, then available. Otherwise, otherwise, um, otherwise, I have to wait. I have to wait in a sense that not busy wait, but efficient wait. Doğancan has a question. If Dijkstra invented semaphores in 1965, what is the point of Peterson's solution made in 1980? That's a very good question. So what is your guess? What's your guess? I have already, we have a very good solution with the Dijkstra. Yeah. So Doğancan, that's a very good question. So why do we need to have Peterson's solution 15 years after much more efficient solutions of semaphores are invented? That would be a good midterm question, actually. Let me copy it. I will copy this one. I will copy this one and put it to my, email it to me. No, maybe, how am I gonna, okay, just email it to me. Yeah, I will email it. Somebody's typing. I need the answer for this one. That's a very good question. Okay. Last question. Yeah. Okay. So the answer is ontogeny. Well, yeah, well, Yusuf, that's a very good answer too. But yeah, but that will not get you very good points in the midterm exam. Yeah, that's the actually answer. No, the first one is much better. Ontogeny recapitulates phylogeny. Yeah. The thing is that, remember, what do we need for the up and down? We need operating system help, right? How does the operating system achieve checking, decrementation, and sleeping in the atomic way? It needs help from the CPU. If the CPU doesn't support it, let's say in 1981, you have the Intel 404 processor, right? That processor, I bet, doesn't support any exchange instructions, right? Exchange instructions or TSL instructions. So you need to find a solution that can be implemented using regular instructions. Then in that case, I need to go back to the beginning of the computer science and use whatever available in there, right? So use Peterson's solution. Peterson says that, of course, busy waiting is not good, but if the CPU doesn't support any atomic instructions for TSL, and my operating system doesn't support up and down, what am I going to do? I have this nice compact solution, and you can use this solution on your PCs. Okay? So both of the question and the answer was good, but again, Yusuf, if you say the answer is ontogeny recapitulates phylogeny, that will not give you very good. That will not get you very good grades. You need to explain it a little bit. I bet you had the idea, but okay, good. So that means that this online teaching thing may work. I don't know, but I hope the other people's are. I still have 77 people. Okay. Good. I don't know who these 77 people are, but maybe some people from Gebze Yeni Mahalle. That's okay. My sister is watching my videos too. Abla, are you there? Abla? Maybe she doesn't. She just comes in and puts a like and goes away. Okay. So let's say implementing so I need to implement up, down, and up. Okay. It is typically done in the kernel. A question and answer to you Who asked this question? Yasir, this is your question. Typical done in the kernel, but you don't have to. While I am implementing this, you must interrupt or disable the memory bus on the multiprocessor test and set lock protection as well. Okay, it only takes only a few microseconds. So we have a visitor.
Oh,
They don't see you.
they didn't see me.
Yeah,
No,
because
that's
you need to go there.
Where?
Just it's a delayed. Just stay there. Just a few seconds.
It's over a minute.
I have a delay of 30 seconds, maybe
30 seconds. Oh.
more than 30 seconds. But you know, the operating systems are like 60-year-old stuff. So we are not in a hurry. And this Corona thing is going to stay for a while. So this is what we do. Okay, so the implementing of the semaphores is usually done using test and set lock protection. And it gets lots of help from the hardware, and the CPU knows about it, and the operating system knows about it. For the Patterson solution, it's a software-only solution. It's a very nice solution. But it uses the spin locks. Okay. Good. So this is the solution for the producer-consumer using the semaphores. Okay. I need 3 semaphores. One is a mutual exclusion for the critical region, entering the critical region and leaving it. The other one is a counting semaphore. It will count the number of empty slots. At the beginning, I have n slots, and I have another semaphore that counts the number of filled slots. Okay. So I have total of 100 places available at the beginning. N is 100. Infinite loop and infinite loop. Okay. So produce item and consume item is here. We are doing all of this stuff just for these two. Produce and consume, produce and consume. Of course, whatever I produce, I need to insert. Whatever I consume, I need to remove it from the buffer. Okay. So this is my critical region. Down, empty, and no. Critical region like this one and this one. It's a mutex. I down it. If it is 1, I make it 0, and I enter the critical region. I insert my item and exit. I up it. This one says that down. If it is 0, then it's going to sleep, right? So I will sleep either here or there. That's one possibility to sleep. The other one is this. It says that as a producer, I need to decrement the number of empty slots first. So decrement is empty, which is 100 at the beginning. Since it is not 0, I will down it. I will decrement it. I will down my mutex. I will insert my item. I will up my mutex. But see, I don't up my empty. I up my full. Full says that. Okay, full says that at the beginning, the number of filled buffers is just 0. So I incremented full. Why am I doing this? Because this guy is down, it's decrementing full. It says that I will decrement full, which is 0 at the beginning. So at the beginning, consumer will be blocked. It will go to sleep. Okay. It will sleep until somebody produce something and incremented this one. Okay. This one will not enter into this region before somebody makes this full, at least 1. Okay. And after that, it will say that I need the critical region mutex. Then I will remove the item. Okay. Up mutex. Then it says that I will up empty. I will up empty. If empty was 0 before, that means that somebody is waiting on it. Okay. So it ups empty. Okay. Good. So this is the whole solution. So somebody's asking me, yes, kinda. Is that my sister? S2MLE 100 Lesh? No. Somebody's making fun of me. I think I will kick this out. I will kick this person out. If this one is my sister, then well, I don't want to be disrespectful. I will call my sister. Take care of this one. Maybe I will call my sister after that. No, I am out of time anyway. S2MLE 100. I don't know what this is. Okay, I will kick this person out anyway. Add hide user on this channel. No, okay, no, I will not. That's okay. He or she didn't say anything bad. So this is the whole consumer producer thing, and let's see if the places where we can sleep. Where are the places that we can sleep? This one is sleeping. Yeah, right. Sleep can happen only with the downs, right? Sleep can happen only with the downs. This one sleeps. Okay, and this one. There are 4 places. There are 4 places where you can sleep with this example. When this one is sleeping, that means that there are no empty slots available. It is all filled up. When this one sleeps, it says that the consumer full. It says that there are no items inserted inside the buffer. I need to wait. Okay. If this one is sleeping there, okay, this one is sleeping here, then I need to make an up call with the empty. Okay. And if I am sleeping here, then this one will wake it up. Okay. So why do I need empty and full? I need them to take care of the buffer. If I have empty space and full space and etc. I am using semaphores to get help from the operating system. Okay. So empty and full are for that. Mutex is for entering the critical region. Question. If I remove this one, no, let me make it, okay, remove this one, this one, and this one. Would it work? Would I have race condition in this example? I don't understand what up and down function does. Oh, okay, let's go back to then. I mean, Ali Emre, the definition of up and down are here, right? Up just increments this one, down just decrements it. But there are exceptions. When this one is 0, down doesn't work. It just doesn't decrement it. It just goes to sleep. Okay? Who wakes it up? Somebody that increments this S1 wakes it up. And up says that I am going to increment this value. If somebody is waiting on it, then I will wake them up. Okay? Up never sleeps. Down sleeps. Okay? Down never wakes up somebody else. Up wakes up somebody else. Okay? Ali Emre, is that okay? It's not, I mean, if you look at this example, this should be clear enough. This will go to sleep if MEX, mutual exclusion, is 0. Okay, this will go to sleep. It will not enter this critical region unless somebody makes this MEX variable non-zero value. Who's going to make it using okay? Okay, good. So let's any answers to my question. If I remove these mutexes, if I remove these 4 lines, what happens? Do I need them? Because I already have 2 semaphores and they are good for synchronization race conditions. Why do I need these mutexes? Is there any way I can save all these questions and everything in the YouTube video? I don't know. Any answers? Why do I need mutexes? When you answer that question, I will ask the other question. Why do I need empty? Why do I need 2 semaphores to count the number of empty slots and full slots? Okay, maybe I should stop here and I will start tomorrow's lecture with the answer from you why we need those mutexes. Okay? So that's it for today. If you have any questions, I will stay here for a while and I will try to answer them. Again, you may call me from my phone. Yasir is giving me an answer. Aren't the empty and full used to keep the size of the buffer and mutexes for the critical region? Yeah, that's true, but I need to down empty and full anyway. They will be blocked anyway, so why do I need the mutex? It can be read white buffer. I don't understand what you mean, Emre. Yeah, Yasir is on the right track. I mean, keeping the size of the buffer is something that we need to do, yeah. Yeah, Antonio, the stream will be saved to YouTube, but so you mean that let's let the people watch the stream video, not the uploaded video? I am not sure about the quality of the saved stream because unfortunately our internet connection at school is not that good. I get breaks from time to time. So people need to go to the stream then, maybe, yeah. I hope. Okay, we will do it that way. Oh, maybe I can do this, okay? Maybe I can do this. Just open the YouTube and go to live. And in that place, I have the comments in there. And if I do this, well, it doesn't look like I have many questions. Oh no, it doesn't keep all the questions, all the chat. Maybe go to my channel. Anyway, I think the stream save will be good enough. Okay. So I'm looking at the question now. In this example, mutex can be 1 or 0 while full and yeah. Okay, so Yasin, those are good answers. We will continue with this tomorrow then. Okay, I'll see you tomorrow. And I will be here for a while, as I said. Let me go get some tea. And if there are any questions, I will answer them after that. I will stop the stream. Okay, thank you. I guess no questions. Okay, thank you then. See you tomorrow.